Mr. Robertson used the term chemically bonded, but I should point out that other synonymous terms that are used as precision sand, as used by the automotive powertrain divisions, they use the term precision sand commonly, but it could be typically those systems would be phenolic urethane cold box systems, and the majority of the examples I will point out would be using that type of chemically bonded systems, but I will make reference to some other chemically bonded systems as well. So to get going, first of all, I want to talk about the thermal distortion testing technique, often referred to as TDT by its acronyms. And there are several papers that relate to the procedures, how this works. We'll show you that briefly today, but if you're interested, an important paper, the next generation thermal distortion test, was given in 2013 at the Casting Congress, and it could be found in AFS transactions. But thermal distortion testing is really a measure of expansion, contraction, and degradation experienced by a mold core composite under extreme heat and liquid pressure of that molten metal. The important issue here is that pressure is introduced into this test. We have had different postulations for distortion in castings, and certainly there can be multiple postulations. The one that I will present today is primarily based on mechanics. But if we look at pure heat certainly will produce expansions, especially in materials like silica sand, that we go through relatively low inversion temperatures as low as 1150 before expansion, exponential expansion, going to phase transfers from alpha to beta quartz, cristobalite to midomite at temperatures closer to 2700 degrees Fahrenheit. But we believe that some of these anomalies that we see as veining or penetration can happen at much lower temperatures. And that's why we have been studying this thermomechanical approach. On these pictures that you see on the slide, there are scanning electron see anomalies at the center, crack propagations. These crack propagations can be magnified, and if we focus in on one spot, we can magnify that further to see the breaking of a binder bridge. If that binder bridge is broken and there's a crack, we believe if that crack propagation is wetted, that's where we could see veins or penetration phenomena. So certainly defects such as expansion, oversized castings, distortion, penetration, veins, or sometimes called rat tails, can occur. But the mechanism of occurrence in a chemically bonded or precision sand will be different from that of green sand. Okay? And our discussion here will be primarily for chemically bonded sand. This particular slide shows us the classic rat tail or veins and penetration on surfaces of castings. And typically iron, at iron temperatures where we're dealing. Next, I want to share with you a schematic view that idealizes the representation for the thermal distortion test on the cross-section. It shows a hot surface, and typically for the test that I'll be describing today, we'll maintain that hot surface at 1000 degrees steady state, plus or minus 3 degrees C. And a dish-shaped specimen that is typically 50 millimeters in diameter, and the specimen thickness, we could vary that. It could typically we have it at 8 millimeters thick, but we can change that thickness to 10 millimeters, 12 millimeters, if we needed to study different wall thicknesses in a casting. So this particular specimen is brought in symmetrical contact to the hot surface, and that specimen is only supported around its periphery or circumference 1 millimeter. So that specimen, after it's supported about the hot surface, will be free to bend. It's in compression at the hot surface, and it's being loaded, so there'll be a tensile stress on the opposing surface. Okay? Next, we want to show you a video rendition of how loading takes place in this semi-automated means of testing. So the specimen is loaded in direct symmetrical contact with the hot surface. That hot surface is maintained at a steady state condition, and we bring that specimen to represent the head pressure on the casting. We are sensing temperature at the back side of the specimen, and we know the temperature at the tip. We're also measuring dimensional change radially as well as longitudinally. So we have a three-dimensional representation of what's going on this specimen, dimensionally as well as thermally. And we collect that data in real time. As you can see on these graphs, they are collecting data thermally at the hot surface, at the back side of the specimen, so we can get thermal gradients. We are measuring radial change and longitudinal change on the specimen. The specimen does remain intact after testing, and we can observe a heat-affected zone where we can see pyrolyzed sand. Next, I want to explain how we interpret a distortion curve. So a distortion curve, an idealized distortion curve, is shown here. Displacement will be measured on the vertical axis, and time as a function of temperature, that temperature is steady state, is over 90 seconds, because for our experiments, we were representing a medium-sized casting with approximately 150 inches, 150 millimeters or 6 inches head pressure. And that particular casting from simulation analysis skins over in 90 seconds, so it's not necessary to collect data longer than 90 seconds. But to explain this particular thermal distortion curve, the origin, excuse me, I need to back up here. There we go. I can get this slide to advance. You can see there is initial expansion in a specimen, and that is when that specimen is brought into symmetrical contact with the hot surface. Again, we are supporting that specimen only on its peripheries. That specimen then would be free to move. It can move in expansion, and that's initially what that initial contact will show. Expansion that is shown from D0 to an expansion documented here. Next, the initial thermal expansion over time will show the undulation of plastic deformation, expansion, plastic movement as the specimen sags around the hot surface. All of this is recorded in real time. Okay? And different sand binder systems exhibit different thermal distortion curves. We measure the total distortion as the absolute value of the arithmetic sum of the changes in distortion. So we can represent that as total distortion, or we could break that up into what we see as expansion and what is plastic deformation. Further, the specimen remains intact, so we could take observations at the heat-affected zone and see what has been occurring. Okay? Next, let's take a look at the specimens before the elevated temperature test and after the elevated temperature test. After thermal distortion test, we can see the pyrolyzed sand at the heat-affected zone. If that loose sand now is removed by a light air pressure, approximately 2 psi, we can see what occurs beneath that heat-affected zone, which are anomalies like crack propagations. But more importantly, that compression surface is only evidencing one aspect of this mold or core material. And if we flip that specimen to the backside, we can see that that crack propagation could actually transfer to that backside. And further, the pyrolysis that occurs, we know that there will be heat transfer at least 1150 degrees Fahrenheit, but we are recording that temperature because we are seeing charring. Okay? So these observations can be made from the test specimen. To give you a more global view of what we're doing in the research project, we are not just doing a laboratory top test, we are also conducting casting trials. Why? Because we know foundry engineers like to see what's happening on a working casting. And one of the classic experiments that we ran several years ago, we used one type of sand, one binder system, but we changed just the binder chemistry. So we are using in this experiment a shell, a phenolic urethane cold box, a furan system, an alkylate isocyanate oil at a 2% binder level, and the same round grain silica. We had evidence shown in the third column from your right, showing what we'd see in thermal distortion testing. The specimens at their interface show differences, but in casting trials on the compression surface of the same specimens behave differently, as opposed to the tension surfaces of the as-cast specimens, where we could observe either certain types of casting defects, such as veining penetrations or not. So we know that there were differences due to the chemistry of these binder systems. To evidence this further, we want to look closer at the thermal distortion curves for these same systems. And here we are showing, again, displacement or distortion on a vertical axis. The absolute, the origin is shown here over 90 seconds time. Again, the same test parameters were used, the same length of time, and each of these sand binder systems, remembering that the binder content, the sand type is held constant, it's just the binder chemistries are different. The furan system is showing purely expansion. The phenolic urethane cold box, or a PUCB system, is showing initial expansion and followed by plastic deformation. And both the shell and the AIO, alkylate isocyanate oil, are remaining relatively steady state over the test. Still, there is undulations, secondary polymerization going on. We can account for that. But the main point here is not to indict any binder, because nobody is going to be using at iron temperatures maybe 2% shell in that system, or the same may be true for alkylate isocyanate oil or other systems. The main point here is to have you understand that a major cause of mole wall movement are the chemistry difference in the binder systems. So taking that idea further, we wanted to look at our specimens themselves. Why? Because these specimens can cause variability in the test. And if we could reduce the variability sample to sample, we certainly can attribute issues of distortion, issues towards veining and penetration issues, mainly to testing parameters. And what one of the problems were is the fact that when we did some X-ray CTC imaging of specimens to look at density differences, we saw that that was clear from a gate location, as I'm pointing to here, all the way across the specimen to where a vent location would exhibit. The brighter colors are showing higher density in the specimen. The lighter colors are lower densities. We saw a resin-rich area where the density was high. And this resin-rich area in this 1% cold box system that was blown at 60 psi was always causing some distortion. But that was not the only problem with the way that we made specimens in days gone by. We had a parting tool that left a parting line, a raised parting line, on the dish-shaped specimen. Here I'm showing you one uncoated, and then one that is coated with a mica graphite refractory coating at 34% solid, and you can clearly see the parting line on this image. This particular raised parting line was caused by the tooling that we use. On this slide, I'm showing you the tooling. It's a two-part toolbox that produced 3 specimens simultaneously off a blow. It's vertically parted, and because of that raised surface, we could pick up that particular differential during testing. Why? Because in thermal distortion testing, we can measure or see the sensitivity or resolution in our measure plus or minus 1/10,000 of an inch. So that raised parting line was not helping. So we had to develop a new tooling design. This particular new tooling design was one that was developed here at Western Michigan University, but supported by ASK Chemicals. They own this particular tooling, and this particular tooling design prevents the raised parting line, and it also has some scratch venting that I'll show you here in schematics. So there is a scratch venting surface, just a couple thousandths of an inch around the specimen, both on the top surface as well on the back side. This particular plate, central plate, is flat, and it does not have a true parting line on the specimen. It allows us to make a 3 or 4 specimens simultaneously. There is this particular core tooling was studied, and some of these pretty pictures was also produced by one of our alumni that worked for ASK. He did simulation studies to show core blowing and fill of these sand systems to show that there was uniform fill by changing the vent relationship, as well as the improvement of the density profiles, where we're only getting higher density closer to the gate. We can't really avoid that, but still the specimen density is more uniform. And then when we looked at velocity vectors for filling, we saw that this was uniform and filling the specimen uniformly and true. And same as we applied the T-gas effect to cure the specimen solid, that flow front was traveling and flowing out through the vent scratch gate passages. So we were very happy with the new tooling design from a simulation standpoint, but we wanted to see what would happen when we take this into testing and how it would affect the data. So we wanted to test the old tooling design versus the new tooling design, with the primary goal of hoping to reduce specimen-to-specimen variability. So we used the same sand, we used the same binder level, but we're changing just my slides went a little bit too far. Back up here a little bit. So when we looked at the results from our study, what we found with the old tools from some initial tests that we used to characterize the disc-shaped specimens, we use specimen weight, we use the disc transverse strength to get some mechanical properties, we do an impact test to measure toughness, permeability test to measure the venting characteristics, so to the MQI, it measures the venting characteristics, has a physical property, and another a physical property is the abrasive losses on the specimen. And we compare that with the old tool to the new tool. The main difference can be seen with the differences in standard deviation. We found typically that the new tool always had lower standard deviation. That was very important for us in characterizing these disc-shaped specimens. So if we could reduce those variability in the test specimens, it bodes well for thermomechanical studies. And when we went and looked at thermal distortion data, we looked at the longitudinal movement of the specimens from the old tool, and if we compare that to the new tool, we saw that variability reduced. The thermal distortion curves got tighter. When we looked at that radially, here is the old tool. When we looked at the new tools, we saw that these radial movements, they almost superimpose on the line. So we were reducing variability, and we were happy with that. We saw these particular improvements actually helping us to account for less than 0.25% change in binder levels. But what can be more important than even the thermal distortion curve data is what are some of the observations we can make after and during the test. For example, crack propagations or the anomalies that we see at the heat-affected zones. We can account for the time that these crack propagations can occur in our sand binder recipe with or without certain types of additives. Also, the laser cameras that we're recording this particular process allows us to account for other observations, such as the time until we see smoke formation, other types of deleterious consequences like that. But since I'm not really relating things to environmental consequences, I'm not going to say too much about that today. But certainly, the other things that we could represent are a measure of these crack propagations and really what happens at the heat-affected zone with respect to the size, shape, and how we quantify volumetric change at the heat-affected zones for these different sand binder systems. We have the capability to measure that using image analysis software, where we characterize the sand binder systems with these cookie-shaped, disc-shaped specimens before and after elevated temperature testing. So we could account for the differences due to the clean heat source exposure over a head pressure. Again, that head pressure is being delivered due to rho GH. So if we knew the density of the alloy, we could calculate the particular forces that would encounter this particular specimen due to the head height that we're pouring from. We can also study these specimens according to different types of blends that we could mix. Shown at the top left is a disc-shaped specimen made with 100% silica, and down at the bottom left is 100% chromite. We could blend these systems where we have 80-20 relationships, 60-40, or 50-50 mix. And we could also add the many other types of sand additives that we could put into a sand binder systems to study the effect due to thermomechanical movement on the system. Also, I want to make some mention of coating, as coatings are an important technology in the prevention of veining and penetration defects in our industry. And several of my colleagues, who I should mention, are very important in these studies in the 4F committee, are coating experts. They prepared for us standard types, I would say generic coatings that would be micrographite based, that we can deliver to these coatings, deliver these refractory coatings to these disc-shaped specimens. But I want to point out some important issues on these coatings. Naturally, these particular studies took several years, and in a 1 hour presentation, I don't have enough time to cover all. But let me cite an important reference. That is wet to dry, complete coating control, circa 2011 in the International Journal of Metal Casting. That is a comprehensive work that covers the research done by the 4F Committee for AFS on coating control. But what that committee found as important is that we must have a proud layer. That's the layer above the layer of the sand surface that must be in place. And that then we must have an interlocking coating layer that needs to account for 3 to 4 grains of sand if the average particle grain is 300 micrometer, or approximately a diameter on the specimen about 20,000th of an inch. We need to have that for interlocking in that penetrated layer. That is important, and I'll show you why. But the other important thing is that we need to have a common way of coating. If we had different operators dipping specimens and shaking them, the dip time could change, the amounts of shake could change. That will affect wetting and leveling of our coatings, leaving drip marks as defects on that coating surface. That had to be controlled. So we accounted for that in the preparations of these coated specimens. And what the 4F committee did is exhaustive work to show that certain control measures, like the Borme gauge, that is still common in our foundry. I'm not going to show one because we certainly don't believe that a Borme gauge is designed for these colloidal suspensions that are non-Newtonian in nature. They are subject to variability in terms of how the operator would use them, drop them into these coatings. And the variability we see with these types of Borme gauges, the ranges could be higher than the specifications for coating controls. So our research in 4F led us to believe there are different techniques. And since we know that the chemistry is changing with the levels of surfactants, we can have the same solid levels, but our surface tension issues can change, our leveling properties, and the amount of coating in the specimen can change. We realized you need a multi-pronged approach for coating control. We believe there's the big three. We need to look at the solids. More important than Borme gauge is just taking a weight per volume, weight per gallon, let's say. Or look at surface tensions, issues measured by Hercules rheometry or by leveling index. And if we get that type of data, we can account for data in the coating as we dip over time that changes the solids, that changes the chemistry from 8 a.m. to 9 a.m. to 10 a.m. That particular control we can measure as well using surface energetics. In this particular slide, we are showing you two different types of sand on our cookies. One is fine grain, one is a coarser grain. So here's about a 80, 85 GFN, here's a 50 GFN. And surface energetics, by dropping the coatings on the surface, we can measure the wetting angle and show that there is differences in how these coatings could wet and ultimately level on those surfaces as measured by other instruments as well, gloss indication. So coating control is very important, and we need to know how much we put on there. For example, if we dip differentially, here is a 1 second dip time, the amount of coating, the depth of penetration. If we section the dish-shaped specimens, we can see there's differential amounts under magnification, 1 second to 6 seconds. All of those are changes. The next thing that we want to show you is that of venting characteristics would change. So this particular graph is showing you coating deposits. Above the origin here is the proud layer in black, and then the subsurface penetrated and interlocking layers in red. And what this graph is pointing out very clearly, the more coating that we have proud to penetrated, the lower the venting characteristics. So as we look, there's less coating, more venting, and we need to have venting. Venting is important to get gaseous materials that are generated from these carbonaceous binder systems up and out through our metal. We did further work to show the relationship between permeability and MQI. So let me explain a little bit because I'm looking at the proud coating layer in this particular graph, just the layer above the sand binder system on the dish-shaped specimen. Permeability is measuring the venting characteristics as we force a given volume of air through the sand specimen, keeping barometric pressure and temperature constant. The MQI is doing a similar thing. It's measuring the venting characteristic, but it's using a constant flow rate, and it's looking to the resistance of that airflow through the dish-shaped specimen. So what we see in this measure is that there is an inverse relationship between permeability and the MQI for the coating deposits. As permeability numbers go down, the MQI goes up, and vice versa. So we have characterized that for the proud coating layer. And we see the same trend is true as we increase the dry weight on the loading of our sand binder systems. The permeability and the MQI are inversely related, and we have documented those relationships. What we have also done is found a way to measure hot permeability. This is some work that is currently being done at Western Michigan University. And what we found very interesting here is that as we heat the specimen, the permeability on the same sand systems can change 15 to 25 permeability points. It's very hard for me to describe a unit of permeability, but what we're saying here is that these particular permeability ranges that changes as we heat these specimens could be the differences between using a coarser sand, like a 50 GFN, to a finer sand that is 80 GFN. So it could be some opportunities for the foundries to get better venting by potentially using less binder and then having some savings in economics. Those could be some beneficial opportunities. But we are doing some more work there to understand. But certainly what I want to point out here is that there is differences when it comes to surface anomalies. On the top row on this slide is showing you the chemically bonded polyurethane cold box specimen that is uncoated, then exposed to thermal distortion testing, where we have blown away the loose pyrolyzed sand to expose the heat-affected zone, showing the crack and the cavity of pyrolyzed sand, and on the back surface the crack. But when we use a refractory coating of a known solid level, that coating surface remains intact at the heat-affected zone, as I'm pointing to here. But on the back side, we still see pyrolysis, where the heat transfer has gone longitudinally through the sand and radially through the sand, and that crack propagation is showing the same way as the uncoated specimen. Now, what does that mean? It means that the coating is preventing potential erosion, penetration types of defects. As I'm going to point out by this video imaging, I'm using 20 psi now to blow off that heat-affected zone on the coating, and if we could blow that coating away with higher air pressure, you could see the burnt pyrolyzed charged sand is exposed and will be taken out. Okay? So the coatings do work to prevent the veining penetration issue. But what else? So if we section these coated specimens, here is some section specimens at 38% solid. So the cross section blown away at 20 psi. This coating is still intact. It's a lower loading, and then at 40 psi we have blown at 40 pounds per square inch. Before elevated temperature exposure, this pyrolyzed region beneath the heat-affected zone, we still have 40 to 60% of the loss of ignition still present. So there are still high amounts of organic materials in the sand, but the coatings do remain intact. But if the coatings cannot vent, the gases that are formed from these organic materials could cause these coatings to separate, delaminate, okay? Because the binder levels, the binders are burning off, gases need to vent up and out, and that is causing certain issues on these brazed surfaces of the coatings that are intact here. Okay? I should go back and point out on the last slide that you can see as we increase the percentage solid, and if I back up to the previous slide, there is a thinner layer or proud layer present. You can see that as we change the solid level on this refractory coating. But what happens in thermal distortion testing? Here is uncoated discs compared to 42% solid, 38% solids, 34% solids. As we look at the origin, we see some initial expansion followed by plastic deformation. Over time, at the same head pressure, at the same temperature, at the iron temperature, we are seeing no difference, coated or uncoated, when it comes to distortion longitudinally and radially. What does this mean is that there is no difference in expansion and plastic deformation for distortion. We know that the coatings prevent the penetration and veining issues, but the coatings, this generic coating does not prevent distortion. We will have to engineer coatings to possibly insulate, to change these refractory properties at the mold metal interface if we hope to improve distortion. Okay? The next important thing about our work is to show you that we can back up in terms of what we do on laboratory tests, in controlled laboratory conditions. We could do it in mold, in casting trials. This particular slide is showing that a schematic of how we can wet in compression a dish-shaped specimen, the same 50 millimeter dish-shaped specimen at a given thickness. It could be 8 millimeters, 10 millimeters, 12 millimeters, etc. But we are wetting at a cross-section same as what we were heating in thermal distortion, 20 millimeters in diameter. And with a delay, we wet the compression side in tension. What do we see? We can pick up then from what we have evidenced in laboratory tests in the actual casting trials. We can show you a vein or, depending on the sand binder system and chemistry, a potential penetration. The mechanisms are the same. It depends on whether or not the sand binder system has that brittle failure, crack propagation, or if it's a more plastic, elastic movement of the sand that reduces the density that we know can penetrate. And a schematic of how this casting trial works is shown on this video clip. We are wetting one side at a given head pressure and temperature in tension, and with a slight delay, we come back and wet the compression side. On the the tension side. And the tension side is where we are seeing typically the anomaly of veining and penetration. But we have other casting trials as well. In fact, we have 4. But before I point out other types of measures, we want to show that we can evidence through image analysis, just like we did on the dish-shaped sand specimens, the image analysis for change on those specimens. We can do the same from the casting trials. For the metal surfaces, we can have idealized representations of the veining or penetrated surfaces and account for those differences. We have 4 casting trials that can stress the specimens in tension and compression. We can have casting trials from the same head pressure. We could change head pressure and loading. We have casting trials where we can record in real time the distortion on the tension surface. And to show you how this works, again, we'll pour from a standard head pressure, typically through a sleeve and filter combination, to wet a specimen, 4 of them simultaneously, and using linear variable transformers at the back side of the specimen on a tension surface, we can record in real time, like we were doing on the thermal distortion test, what is happening longitudinally to the specimen and account for the distortional movement of the various sand binder recipes that we might want to talk about in real time. So with those particular thoughts and ideas that are emerging from our research and development in 4F, I thank you for your time and look forward to your question with the remaining time that we have. Thank you very much.
Okay, Tom, if you're ready, we can start answering some of the questions that came in during the presentation.
Okay.
Sorry, just give me a minute here while I just pull some of them up.
Yes.
Okay, first question is from Jim Furness. He's asking, explosive delamination of coating is permanent. If permanent is too low?
Can you repeat that, please? I didn't
Maybe we want to have him voice his question because it's kind of paraphrased. It says explosive delamination of coating is permanent. If permanent is too low.
Okay, I'm going to guess at the nature of that question. If we don't have a proper wetting of that coated layer, proud and penetrated, we would experience spalling defects. That coating wouldn't remain intact. And the same types of defects that we could get from an uncoated surface, the coatings can cause. The important thing is that we should engineer the sand binder system properly to prevent movement. We want thermal stability, because if that underlying sand composite moves, so too would the coated layer, and we will end up with the same defects. The coating is a band-aid for distortion, but with proper application of proud and penetrated layer on that coating, we could prevent some of the erosion types of defects, penetration and veining as well. But for right now, the coatings that we study are not preventing distortion. Okay? They have to be engineered for that.
Okay, Jim, you're unmuted if you want to voice. I see you had a couple other questions, so you can just go ahead and voice them.
Yeah, Sam, what I was really talking about is that we're seeing a defect where the permeability is low, and that two-stage permeability you were describing, we're seeing explosive delamination of the coating, and I think you're kind of describing that. You get a softening of the binder, the gases can't escape, and then it completely blows the coating loose off the surface of the core.
Correct.
And that's kind of what I was saying.
Right. There was a specimen that I showed. If I have access to go back to that one, I could probably let me see if I could find that specimen and
yeah,
show
I think
you.
You were showing that.
Yes, I was.
Delaminating.
Right. It was especially this one.
Right there.
Right here. It was showing that there's a delamination because that gas is not being able to vent through, and it's affecting things. That coating moves, and ultimately that will change the dimension of that casting at the interface. Yes. So that's correct, Jim.
Thank you. The other question I had, Sam, was we've done some work with creating a partial vacuum at the initiation of the blowing of a core, and when you showed differential density across the core, what we've identified as you're blowing into a core box is that air from the blowing of the sand is hitting the edge of the core cavity and flowing backwards and creating turbulence in the sand and creating differences in density, and just a partial vacuum across the core box solves that. And I was wondering if you've tried that or looked at that.
Yes, certainly. Density differences in the core or mold materials have shown up in distortion on casted parts. There was a paper published, I can't remember the exact date, but the author of the paper was John Lanuti from The Ohio State University, and this is circa 2000. He has pointed out this particular type of issue very well in chemically bonded sands. The density differences caused by venting. There's a resin wipeout that occurs as we blow, especially at higher pressures. The resin binder wipes out towards the vent location, so we get a resin-rich area there. Right? That idea is kind of like trying to blow through a straw and plug the end. And if we put a pinprick, where is the saliva going to emanate? Where we put that pinprick, right? So basically, the binder is trying to get there, and where you get higher binder levels, that actually is worse for us. So what I'm saying is higher binder levels is actually less. It's worse for us. is actually contributing to more potential distortion issues on castings. And that was the work that Dr. Lanuti, I helped co-author that particular paper as well. That was done circa 2000. So that was pointed out there.